Hi, this is Professor Pope with Xavier University, and today we're going to be talking about 5-6 higher degree polynomials and rational functions, and this is indeed our last section for this course. So we've made it. We're almost done. We have a lot of definitions and writing, so get your pens ready. You may want to pause now, write down the definition of the polynomial if you haven't already, and then come back and I'll start with examples. All right, you should be back by now. If you've even paused. Polynomial, this is basic, but just to make sure we understand, we use these terms. A polynomial is a function whose formula can be written as a sum of powers. So I have a few examples. A polynomial may look like a single term 5x, or maybe you would have 5x cubed plus 3x squared. This would be a binomial. First one would be a monomial. Or maybe you'd have 5x cubed minus, 17x squared plus 13x plus 11. This is also a polynomial. We see we have the sums or differences of power functions. All right, so having said that, we need to also remember what the degree of a polynomial is. And the degree is the highest exponent that occurs in the polynomial. Okay, so if we looked at this monomial here, 5x, then the degree of it would be 1, because that's what the highest exponent here. It would be 3 for this binomial, 2 for this trinomial. It's the highest degree, the highest exponent is the degree of the polynomial. So a cubic function, obviously the degree of that would be 3. A quartic function, the degree of that would be 4. Some other definitions we need to know before we can really get started. Asymptotes. I'm sure you've heard of these, but an asymptote is a line to which a graph gets closer and closer and closer to, but never actually touches. You have to excuse my sloppy writing. So we're going to be looking at horizontal and vertical asymptotes today. So just keep in mind, this is when it's a certain line that will be on a graph that it gets closer and closer and closer to. Oftentimes, the x-axis or the y-axis serve as asymptote for certain graphs. So the first one, let's talk about what they call poles. Vertical asymptotes are often referred to as poles. So I want to make sure you know both ways. You may be asked to find the vertical asymptote, or it may just say, what is the pole of this? So a pole, it would be a vertical asymptote, so it's going to be a vertical line that the graph is getting closer and closer to. And this occurs when the denominator of a function has a 0 that the numerator does not have. So let's write that down. Occurs when the denominator of a function has a 0, but the numerator doesn't have that same 0. So I'll give you an example of that. So let's say we were looking at the rational function x over x minus 1. So this binomial at the bottom, we have x minus 1. The pole here, or the vertical asymptote, what do you think it's going to be? X equals 1. The reason is x equals 1 is something that we actually cannot, this function wouldn't be able to be evaluated at, because if you plug in 1, you're going to get 0 in the denominator, which would make it undefined. So the pole is x equals 1, and the graph would get closer and closer to this but never reach it. So take a moment, try and graph this in your graphing calculator, see what it looks like, and see if you can see why x equals 1 would be a pole. So notice x equals 1. That is a 0 of the denominator, but it's not 1 of the numerator. I can have 1 here that would not make the numerator 0. All right, let's now look at horizontal asymptotes. And this is the limiting value. We've already talked about these when we talked about carrying capacity and limiting values, and when we talked about bacteria growing in a petri dish or something. Like, there's only so much space. So if we looked at a graph of that, it would be considered a limiting value would be considered a horizontal asymptote. All right, so yeah, this is the limiting value of the function, and it's a horizontal line that the graph gets closer and closer to but never touches. So our example here, let's look at 16x divided by 1 plus 2x. So what I want you to do here is I want you to, if you didn't graph the last one, make sure you graph this one. I want you to graph this in your graphing calculator. So go to y equals, graph it, then I want you to hit second and graph to look at the table. If you look at the table, I want you to go down and continue going down, 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 increasing your x value. You will eventually see a limiting value. If you go to your table set, so if you go to your calculator and you hit the second window, I believe it is, it says table set, you can set the window to be whatever you want or wherever you want to start. If you put like 1,000 in for x, you're going to see it's never going to get over 8. You'll see that the final answer is 8. That means that's the limiting value. It's getting closer and closer and closer to that, but it actually won't touch it. The calculator can only be so precise, so it ends up just saying 8. But understanding that will be the limiting value. So I have 2 examples for you, and then we're done. Here's our example for finding a horizontal asymptote. I don't remember what example this is. All right, so let's say we have a function f of x is equal to 6x to the 4th minus 5 over 2x to the 4th plus x. So I want you to graph this. When we're looking for horizontal asymptotes, the way we do that is we graph. Graph, look at table, and find the limiting value. Okay, you should be done now and have that in your graphing calculator and have looked at your table, and hopefully you saw that the limiting value would be y is equal to 3. So that's pretty simple, just putting it in the calculator and figuring it out. So for example 4, let's hope we're actually on example 4, if not, we are now. Let's find the pole of this function. All right. So if we want to find the pole, that means we want to figure out when the denominator has a 0 that the numerator doesn't have. So first things first, let's set the denominator equal to 0 and solve. So x squared plus 7x is equal to 0. The way I would solve this, I could factor out my x, and then I'd be left with x plus 7. And these are my two factors. Using the zero product property rule, I know that if x is 0, doesn't matter what's inside of this parenthesis, because if I multiply it by 0, it's going to be gone. So one of the zeros, x is going to be equal to 0. The other would be whatever makes the parenthesis equal to 0. So if I had -7, if I plugged in -7 for x, and as soon as I got -7 plus 7, I get 0. Doesn't matter what happens, it's going to go away. So the two poles here, or vertical asymptotes, would be x equals 0 and x equals 7. And these are both poles because they are zeros of the denominator but not the numerator. All right, those are our two examples. Not much here that we're covering. The problems that I want you to do and bring to class would be S1 through S17. And this is on page 499. These are the problems you may have to, for a few problems, you may need to skim back through the chapter. I didn't cover everything. I just picked out the important parts that I thought some were kind of buried in there. That I know you would need to use. And then when we come to class, we will be working on a few of the 5-6 exercises and then preparing for the final. So thank you and have a good night and a great weekend.